All right, let's go ahead and get started. Let's see, I don't think there's any other announcements. You guys already know what's coming up on Thursday. We're going to have this exam. It'll be in class right here on Thursday. So it's open book, it's open notes. You can bring whatever you want as long as it doesn't use electricity. I don't care. It's up to you. Now, I mean, be smart about it, right? You can bring a book, but having to search through a book to find an answer to a question in the middle of the exam is going to cost you time. So, the more stuff that you've actually prepared for, the better. But whatever you want, bring whatever you want. That's fine with me. We'll figure it out. If you need accommodations, hopefully you've already spoken with Cornerstone. I cannot accommodate extra time in here. There's another class that's right after this one. So if you require extra time for the exam, I unfortunately cannot accommodate you. But please contact Cornerstone as soon as possible, and they can get you set up. Does anybody have any questions about the when, where, why before we talk about what's on the thing? Yeah.
When we come in here on Thursday, I don't know, we have like a big pile of them, just grab it and start going to work.
Oh, I'll pass them out. I'll pass them out when the time happens. I will probably try to get started as soon as I possibly can. So, Thursday's not a day to be late. So I will try to get started as close to 11:30 as possible. Probably won't be 11:30 on the dot, but I'll try and get started as close as possible. Yeah.
I'm a little worried about the classes in here because they tend to run a little
over. That's as close as possible. There are things outside of my control, but I will get us started as soon as I possibly can on Thursday. Any other questions about logistics before I talk about content a little bit? I did post those past exams on Piazza, so give you a feel for the kinds of stuff that I like to put on exams. But let's just do a quick rundown of the potential topics that you might see on this exam coming up. So we spent the first part of the course talking about the database basics, right? What is the database made out of? We've got tables, rows, columns. We've got various data types that kind of feel like but aren't exactly like the data types you're used to with a language like Java. Metadata. What's an example of metadata? Yeah. Actually, that's correct, though. The data types of a column I would consider to be metadata. That is correct. Yeah. Indexes. Indexes are kind of their own unique thing. I'm actually not sure how to classify that as metadata or not. That's a tricky one. I mean, whether an index exists or not would be metadata. Yeah.
A heap pages tuple iterator.
A heap pages tuple iterator. I think that's a little bit too specific. But the heap pages tuple iterator certainly would use metadata in order to do its job, including the data types, how many columns there are, etc. Yeah. Relationships. There we go. That's a great example of metadata. What relationships exist between tables? And that's actually the next thing on the list, right? What are the connections between two tables? So we saw some very, 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 very basic SQL. The clauses that we covered in detail are up here. Select from, where, group by, order by. We've seen joins as well, which is part of the from clause, right? If I didn't ask you about the query, or if I didn't talk to you about the query in class, it's not going to be on the exam. So I see people asking questions about more advanced SQL queries. I'm happy to talk to you about those kinds of things, but if I didn't talk about it in class, it's not going to be on the exam. Use that to your advantage, right? I know some of you know more SQL than what we've talked about. If you're writing a SQL query on the exam and you're like, I should use a subquery here. We didn't talk about subqueries. So, maybe you shouldn't use a subquery here. Maybe you should use what we talked about in class instead, right? Because I'm not going to ask you about subqueries. And if you're sitting there scratching your head like, what the heck's a subquery? Well, it doesn't matter. We didn't talk about them. They're not going to be on the exam. They are pretty cool, though, so if you want to learn about them, come have a chat with me sometime. We did talk about design, how to make an ER diagram, which differs from an actual database, right? The actual database implementation looks a little bit different than what I see on the ER diagram. What's something that I need as part of my implementation that I don't see on the diagram? Yeah.
Foreign keys.
Yeah, I knew you were going to say that. Foreign keys. I don't include foreign keys on my ER diagrams, but I absolutely need them to create those relationships between tables, right? What else might be something that I don't necessarily see on an ER diagram, but is necessary as part of my database implementation a lot of times? Yeah.
Data types.
I'm sorry?
The data types.
The data types. So you actually can put the data types on an ER diagram, but a lot of times we didn't. So yeah, sure. There's another one I'm thinking of that we've seen quite a bit. It's actually, yeah, in the back. A many-to-many relationship, a linking table. Yeah, exactly. We don't see those on the diagram. They don't show up as entities. They don't show up as tables, but we certainly need them in order to implement our ER diagrams. We talked about normalization. So there are 3 forms of normalization. The good news about normalization, if you have a good design, you don't have to think about it too much. Normalization is really only something that you have to actively participate in if you have a crappy design. So if you make a good database design, normalization is not something that requires a whole lot of effort on your part. And then we also saw the SQL that we can use to create tables and insert data into our database. This is the data definition language side of SQL, whereas the basic SQL stuff is the data manipulation side. All right. We spent a lot of time talking about the physical layer. The whole first assignment basically was about the physical layer. So what's a heap file look like? What do I expect to find in a heap file? And then the heap pages as well are a big part of that. How do I insert data into a heap file? How do I get data out of a heap file? Things like that. So I am going to expect you to know that structure backwards and forwards. I'm going to expect you to know how a header works. I'm going to expect you to know the process for adding a new page to that file if that's something that needs to be done. I'm going to expect you to know when you have to do that as well. So that was a huge topic. We spent more time talking about relationships and constraints. So we saw the different kinds of relationships that exist. We've actually already kind of talked about those relationships today. Many-to-many, one-to-many are the big ones. And then for this most recent section, we've talked a lot about relational operations, the types of relational operations that exist. So we've had select and project and rename and all those great operations. And then how do we convert queries into those relational operations? That was a big part of Lab 2. Actually, you implemented the operations and then processed queries. So how do I take a parse tree and turn it into a query tree, for example? Stuff that we've talked about in class. And then lately, the last couple weeks, been talking a lot about indexing. So there are many different types of indexes available. There were 4 different kinds of single layer indexes. What are the 4 kinds of single layer indexes that we talked about? Hint, one of the answers is not a B+ tree. That's not a single layer index. Yeah, what's one of them?
Primary.
Primary. All right, so what's a primary index tell us to do? How does that work? Somebody else? Somebody else? Anybody else? I'll wait. Yeah, in the back. Yeah.
Okay, so if you have, if a heap file has 7 pages, and you have an index about 7 entries. And so you have 1 entry.
That's right.
And then you have a keep value. The data is required to order.
That's right. Yeah, so you're absolutely correct. If I have 1 entry per page, where the entry is based off of the first element from the page. And in order to pull that off, it requires that the data is sorted. The data in the column that I'm indexing has to be stored in sorted order so that I can quickly find those values. What's another kind of index, single layer index that we talked about? Yeah.
A clustered index?
A clustered index. So what's that one like?
That's like a primary index, but you have duplicates.
I can have multiple of the same values in the column. So how does that actually affect the structure of the index then? Yeah.
The index is now only pointing to the first occurrence of the entry.
It's only pointing. It's not one index entry per page now. I can't do that anymore. It's going to be pointing to the first entry in the page. Still stored in sorted order. Yes. Yes. Still sorted in sorted order. So one entry per value now, instead of one entry per page. I'm going to have one entry per unique value in the index. There are two more, although the two are also kind of similar. What's the last kind of index? Talked about primary cluster. What else we got? Yeah. The secondary. And so a secondary index can be both unique and not unique, right? And this is when it's definitely not sorted. And so now that's when it started to look like a bowl of spaghetti. I would see the entries pointing to the actual values, but they weren't in sorted order, so it could be pointing to any page in my file. Cool. And so then we did expand this idea of a single level index and expand it out to a multi-level index, of which we are looking at the B+ tree. And that's what we've been working on most recently. So I certainly will ask you some questions about B+ trees. We spent so much time on them. You know, how do I insert values? How do I delete values? How do I search for values are the big ones, right? But even just general properties like why do I only store data, or why do I have two different kinds of nodes in a B+ tree? What's the point? Why do I have two different kinds of nodes in a B+ tree? Got leaf nodes and inner nodes. Why? Why don't I just have one node type? Yeah. Increases the branching factor. So by having those two separate types of nodes, I don't have to store search keys and entries in the same node, which means that my search keys I can fit more search keys per node, which is going to increase the branching factor, which is going to increase the efficiency, the searching efficiency of the tree. And that's really the goal. We want to make this search as fast as possible. And the more branches we have, the faster it's going to be. And then just last week, or actually it was the week before I left last week, we talked a little bit about query optimization. So I ran you through the steps. I said, here's a query tree. Let's go through the steps and optimize it. So that has a certain set of heuristics, a certain set of rules that we apply. That moves the relational operations up and down the tree in order to create, we're not guaranteeing that we're going to get the most optimal tree. We're just going to guarantee that we've got a better tree than what we started with if we follow those heuristics. I think I've covered all of the topics that we went through, really. Any questions about what what may or may, I don't know what's going to actually be on the exam. I haven't even written the thing yet. But any questions about what may or may not be on the exam? Yes.
Well, you also mentioned in the last lecture that it was the front end stuff.
The front end stuff, yeah, the front end stuff. So that's right. So I showed you how to access a database through a few different methods, using PHP and using Java, a couple different ways in Java. I made you the promise that I was not going to ask you to write PHP on the exam. Although I also suggested that it is possible that I ask you to write Java on the exam. However, if I do ask you to write Java, it's probably more likely going to be related to the homework assignments, not what we saw in class last week. So keep that in mind. Certainly possible that I ask you to write some Java, though, not outside the realm of possibility. And I might ask you to write some SQL as well. So as far as coding goes, those are the two things to pay attention to. Java as it relates to the homework assignments and SQL queries. Any other questions about what may or may not be on the exam? Obviously, I can't fit all this stuff on one exam. We only have like 90 minutes or 80 minutes or whatever it is. So, I do expect you to be prepared for any of these topics. Just because it was on one of the past exams that I gave you does not necessarily mean it'll be on your exam, and vice versa. Just because I didn't ask about it last year doesn't mean I won't ask about it this year. So I do expect you to be prepared for all of these topics. If there aren't any questions, then I'm gonna turn control over to you. We've got an hour left, and I want to work on whatever you guys want to work on. So if there's a particular problem from the past exams that you want me to talk about, I'd be happy to do that. If there's a particular problem from a past class, past homework assignment, be happy to do that. I've also got a whole set of exercises on the rest of these slides that we have not seen yet before, so I'd be happy to find a new type of problem there. I am open to suggestions. Somebody tell me what you want to see.
Actually, this was kind of a question related to the stuff that's on the
Sure,
slide.
yeah, what's up?
I noticed that for the tree, the ones that deal with the B+ trees that had D, which is the fan out, which should be number of children. So I'm a bit confused on that one because it says if they have a D of 2, wouldn't that would be like 1 key and 2 children?
So the way that I talked about fan out was a little different in past semesters than what I discussed it the way I discussed it this semester. So that explains part of what you see. At the end of the day, whether you get the answer on the practice exam absolutely correct or not is actually of less importance to me than getting you to practice. So
I just was like kind of confused on how to do it because like I'm thinking if we only have like 1 key and 2 things, it's essentially a binary search tree now.
Yeah, no, I mean that's not certainly what was intended.
Okay.
On the prior exams. Any other questions or suggestions of what you'd like to do? Yeah, go ahead.
Can I ask a general question?
Yeah, please.
So I'm still a little confused with, so we know metadata is stored in the catalog.
That's right.
Correct. And then the notion of schema and how schema versus the metadata versus.
Okay. Okay, so the question is about metadata and the schema. So what is a schema? Let's make sure we're clear on that first, right? When we say schema, what is that? Yeah.
It's actually the name of a table, and all the columns.
The name of the table, the name of the columns. I would include the data types as part of that. So it's the structure. The schema is the structure. Here is the structure that I expect my data to take. Right? It's going to have this many columns with these data types in it. So that is metadata. Actually, the schema is metadata, meaning that the schema lives in the catalog. That's where it is. If you open up a database implementation and find the catalog, you'll actually somewhere in there find a table that lists, for example, the names of all the tables in the database. And then you'll find another table in the catalog that lists the names of all the columns within all the tables. I'm sorry? You can have multiple schemas in some database implementations. Yes, that is true. We have not actually seen any examples of that in this class, but theoretically it is possible. Yes. The schema of a database is all of the tables that are meant to be taken as a unit, right? So it's multiple tables with multiple columns per table. But all of that information is stored in the metadata. And we saw this in Lab 1 a little bit, where you had to store the names of the tables, right? In the primary key column for that table and where the heap file lived for that table. We didn't go so far as to store all of the column names and data types, although we did store the tuple description, right? Which is basically the same thing. So all of that metadata was stored in the catalog in Lab 1 as well. Yeah, question?
I'm a bit confused about the participation in the ER diagram.
Participation, okay.
Yeah, so for example, in like employee and department example. So if does that mean if an employee so if an employee must have a department or must be assigned to a department, that means that the employee should have like full participation, or I'm just confused about the participation.
Yeah, let's draw a little mini diagram real quick to illustrate this concept. So the question was about ER diagrams and more specifically, participation in a relationship. So how do I draw a relationship in an ER diagram? The diamond, right? So here are my entities. entity B, entity A. And so there's a relationship between these two entities, right? So I have to think about participation on both sides of this relationship. I've got two cases to think about. Does A have to participate in this relationship, and is B required to participate in this relationship? So if I say that A has to be part of this, I'm missing a little information here, right? Which side is the one and which side is the many? So let's just label those real quick. We'll say that's the one side, and this is the many side. So by putting a double line here, I'm saying that every row from A has to participate in this relationship. What does that mean in terms of what I expect to see in the database? How would I know if this participation is being satisfied? If I look at the data in the tables, what would I expect to see to determine whether this relationship is satisfied or not? Yeah.
Foreign key.
A foreign key. I would expect to see every primary key from A show up in the foreign key column from B, right? Every single one. Every single one. Okay? And if there was a primary key from A that did not show up over here, then this full participation is not being met. And you could write a little function or something to verify that that was in fact the case that happened. We could talk about the other side as well, right? So everything from B has to participate in this relationship as well. What does that look like? What does that look like? That's where things get, I think, a little bit more conceptually difficult to wrap your mind around. We're saying that so B is where the foreign key lives, right? We're saying that a row cannot exist in B unless it is tied to A, which is actually true basically of every single one-to-many relationship anyway, right? I can't have a foreign key here that doesn't exist here. It's not possible. I can't have a row in this table that doesn't have a foreign key pointing into A. So for example, if I had this, if I took this out and it was not required participation, I'm saying that a row in B can exist with a null value for the foreign key into A. That's what we're implying by saying that this participation is not mandatory. It's pretty rare to see that. It's pretty rare to see that happen, although not impossible. There are ways that you can implement that in the database if that is truly what you want to do. So the real question with participation has more to do with the one side than the many side. I expect the many side to almost always, not always, but almost always require full participation. Over here is where things have a lot more variance. Maybe it will, maybe it won't. Depends on the application that I'm building. Does that help answer your question? Yeah, in the back.
Two questions. One really quickly on this topic.
Sure.
What was the difference between N and M?
Oh, if I was doing like a one-to-many?
Yeah.
No difference. I would use, I think I would always use 1 to N. The only reason that M would come into play is if I had a many-to-many relationship. So I don't want to put N on both sides, so I just use M instead for a many-to-many. But again, it's flexible. I'm not going to complain if you use 1 to M everywhere instead. I'm not going to complain about that.
And then also, would you be able to walk through one of the B plus tree insertion questions in the practice exam?
Sure.
Either of the practice exam?
Yeah, I'd be happy to. Let me pull those up real quick. Exams. Here we go. Oh, they're on the calendar page. What am I doing? Sorry. All right. This is from the 2018 exam. So first things first, let's make sure that we understand the problem, right? when I say that P inner is 4, what does that mean? What does that actually mean? It can have up to 4 children. What's the smallest number of children it can have? 2. 2. 2 is the smallest number that we're going to allow it to have. If it has fewer than 2 children, then it doesn't have enough children to do its job anymore. And so P leaf equals 2. What does that tell us? The number of values that I can have in a leaf node, the most is 2. So if I have fewer than 2, if I have 1, right? I can have 1 as well, right? 1 is still okay. It's if it goes completely empty that I need to worry about that one. So exactly half is okay. In every example that we've done, I believe that's been true. I can have exactly half of P, but less than half is what dictates I need to do something. I need to fix that problem somehow. And so I gave you a bunch of values, and the question says, all right, make the tree. So what I would like to do actually is give you a few minutes to talk to your neighbors and see if you can get a start on this. I'll give you 5 to 10, and then if you have questions, I'll be around, and then we'll go through a solution up here on the board in a little bit. Yeah, I need to go back and update that one.
Maybe only answer on like assertions.
That's what I mean by maximum credit. If you think you got the answer, then you just put the final answer. I'll give you all the credit. Yeah, I'll do this. Yeah.
So I have a question in this case. So if I have a reply, can I like verify some column that is not in the select?
Yes, I believe technically that is possible. Yes.
Because like this
It's kind of rare though, and you actually do have it in the select, right? Description.
yeah, but what if I want it to be grouped by like the ID first, and then I will show it by like the description, because it doesn't make sense. So what if like 2 items like having the same description?
I see what you're saying. No, you can group by a column that's not necessarily in the select, so that is allowable. Yes. But I would accept this as an answer as well.
Yeah, because it doesn't make sense that it can happen, but
Yeah.
what if they have like the same description?
No.
I haven't started It's very scary.
You'll have too many. This 3 keys. This indicates 3 kids. This indicates 3 kids. I need this. Oh wait. I split this one. I split it.
Excuse me? So if the design like doesn't like give like so much information, can we assume like
Yeah. Sure. I'm fine with people making assumptions. So tell me what those assumptions are.
Yeah, but you got a problem actually for them because the equals 4 is the number of children who can use these. Got one. Oh, it's split earlier. Oh.
All right, let's get started. If you didn't get all the way done, that's okay. We'll do it together. We'll do it together. So first thing I'm going to do is insert a 6, right? There's my 6. What kind of node is this? Oh, I'm sorry, an 8. What kind of node is this? Leaf node. We start with a leaf node. This is a leaf node. Okay, I'm going to put in the 6 next. It's going to go over here. Still a leaf node, right? All right, I put in the 7. What happens? We got a split. I'm full. This guy's full. So I'm going to have 2 nodes. What's going to go in this first one? 6 and 7. Remember, we've been favoring the left side. I can favor the right side. That's not incorrect, but we've been favoring the left side. We had to make a decision. We chose to go left. So 6 and 7, which means that 8 is going to be over here by itself. And now I have to make a new root. And what am I going to see in the root? 7. All right, good. Hook up the children. And this is where we're at after 3 insertions, right? I want to do the 5 next. So I really would like to put the 5 in this node, but I can't. It's full. So I got to split it again. 5 and 6 over here. The 7 is going to be by itself in this node. What do I have to do now? I have to push the 6 up, so it's not just 7 anymore. The 6 is going to be up here as well. And then redraw my links between my children. All right. There we are after 4 insertions, which means we are on the 3. What's going to happen? Another split. Oh, man. Splitting a lot. So I've got 3 and 5, 6, 7, 8. And so what number goes up to the root? 5 does. All right. 5, 6, 7. Now, what I see a lot of times is, like, so for this last one, I have a 3, right? I've got other open spots over here, so why couldn't I have just, kicked some of these other numbers over and put the 3 in one of these open slots? Why don't we do that? Why didn't I try to put the 3 in just one of these open positions that I already had? Yeah.
It helps with the branching factor.
Helps with the branching factor, so that's one advantage, right? More nodes is a larger branching factor. It's going to help me search faster. There's another reason, though. Yeah, in the back.
It also makes insertion more complex and therefore less efficient.
I'm sorry? Makes
Insertion more complex, less efficient, so you're spending more time to save space.
Spending more time trying to save space. That's right. We like having open spots here because eventually we're hoping a value is going to come down that will fit in this slot, which is going to make our lives a lot easier, right? That's part of the trade-offs with the B+ tree. We're giving up a little space. We're giving up a little bit of space with the hopes that we're going to make insertion a more efficient operation. We could insert it so that everything was condensed down, but that would take longer, especially for insertions. So we just did the 3, right? So now we're going to do a 0. Split again. My goodness. Okay. Gotta make some more room. Split again. 0 and 3, 5, 6, 7, 8. All right. What happens next? I take this 3 and I try to put it up here, but I can't. I can't put a 3 in here. It's full. Right? It's full. Remember, P inner is the number of children it can have, but the number of search keys that it can have is 1 less than that. So I've already hit my maximum number of search keys, which is 3. I can't put another search key in here. I would have 5 children, which I can't do. That's not how this problem is set up. So I have to split. I have to split this node, right? All right. So I've got 0, 5, 6, and 7. I'm going to have more inner nodes. I'm sorry, not 0, 3. So what goes in this first node? The 3 goes in this node. What else goes in this node? Any ideas? 5? We're going to put the 5 in there?
No. If we put in the roots, it will not be there. Only 3.
Okay, only 3, because the 5's going to go in the new root, right? And then that leaves us with 6 and 7 here. And so you might be asking yourself, well, why didn't I put, the 5 here and the 6 here? Again, we're favoring the left. I had 4 values. I want to pick the value that's in the middle, but, I go to the middle, and then I pick whichever one is to the left of that. Since I don't have one that's exactly in the middle, that gets pushed up the tree. Got to be consistent. And so then we're just redrawing our pointers. And here's what the tree looks like after the, what did we just do, the 0?
Yes.
Any questions about that? That was the most complicated step so far. Yes?
Just for, if we were thinking about this from the terms of what the program is doing, we can think that it temporarily did have the 3 and the 5 there, but then when you saw we had to create a new node, it would say, okay, get the max in there.
Sure. Yeah, we could think that the 5's temporarily there. In fact, one of the shortcuts that you'll see on B+ trees, if you read the textbook, it goes into this in a little bit more detail. One of the shortcuts you'll see on B+ trees is that actually, if I say there's only 2 values in the leaf node, I'll actually keep an extra slot or 2 over here for overflow, because it helps make the splitting go a little bit easier if I can keep that extra value around a little longer, right? Officially, there's only 2 values, but my list might actually have 3 in it temporarily while I resolve a split. That's perfectly okay. Something you might want to try and look into as you're working on the homework assignment. All right, 9 is next. Where's the 9 going to go?
The last bit.
All the way over here, and I got a spot for it, so that's good. And then a 10 comes in. I don't have any room for a 10 though, right? It wants to go here, so I got to split again, which actually is just sticking a 10 over here by itself. And then, what goes up here? 9. So we got to be careful. This node's now at full capacity, right? The 4, 5, 3. So I can actually put the 4 here, right? Do I have to do anything with my search keys?
No.
No, we're good. We're good. And then last we have the 2. 5, 3. So I want to put the 2 here, but I can't.
I'll split.
So another split. Got 0 and 2 in one node. Got 3 by itself. What happens to my search keys?
Updated 2 or 3.
I'm going to put the 2 up here. And then just make sure my child nodes are updated. And I believe this is the solution to this problem. Are there any questions? Something to consider with this problem, you might have noticed a couple ways, along the way. We talked about this a little bit in class, right? I can't really get a value in here very easily. If I'm dealing with integers, how do I ever get something to fit in here? There is no integer between 6 and 7. This is one of the downsides of a B+ tree, but actually this example illustrates one of the potential problems with B+ tree. If I'm inserting values that are very closely clustered together, that's when I'm likely to have this situation where I've got an empty slot that's not going to be filled. If I have a very large range of values, this becomes less of a problem. Or actually, another way to think about this, we just inserted a whole bunch of values, right? But in the real world, what's going to happen? I'm going to insert a few, I'm going to delete a few. I'm going to insert a few, I'm going to delete a few, right? And so those deletions also kind of help work out any tight clusters of values that you might see in your B+ tree. But it is something to consider. It is a concern, something that is an inefficiency in our tree, having these spots that can't easily be filled. because the values are so tightly clustered together. Any questions? Any questions? Yeah.
If you were gonna go ahead and like delete the 7 from this tree,
Yep.
you take E out of the inner as well.
All right, so the question was about, let's do it real quick. Let's just walk through the process. Let's delete the 7. The 7's gone. What happens next?
Borrow sibling.
I try to borrow from one of my siblings, right? So which sibling am I gonna go to first? I'm gonna go here and say, hey, do you have any values? And this note's gonna say, sorry, I don't, right? So I go this way and say, hey, do you have any values? And this note actually can. So I'm gonna grab the 8 and pull it over here. So now all that's left in this note is the 9. And so the question now is, all right, are my search keys okay?
No.
No. What's the problem? Actually, my search keys are acceptable, right? There's nothing incorrect about them. Well, no, I take that back. If I wanted to find the 8, if I was searching for the 8, it would tell me to go here. No, I apologize. I got a little mixed up. If I wanted to find the 8, it would tell me to go here, but the 8's over here now. So I do have to update the search keys to reflect that this 8 was borrowed. And now this tree is okay. But now I've noticed that we've got a really bad spot. I guess I could put a 7 in here, but I can't put anything else in these 2 spots, unfortunately. Because those values are so tightly clustered together. Any other questions about this? Did I see another hand? Yeah.
Once you built the tree, in the same way that you read the file index, does that effectively file to fill up those spaces?
It does read. So we do have to redo these index trees every so often. Yes, that is true. Basically, what ends up happening is that we'll insert values, and insert values, and eventually we'll see these spots, right, start to build up. It's fragmentation at the end of the day is really what it is, a form of fragmentation. And so after a certain number of insertions have happened, or a certain number of operations, I should say, insertions and deletions have happened on an index tree, but insertions I think matter more for this purpose. The database will say, all right, I'm going to throw the entire tree out and start from scratch. And part of the reason for that is to eliminate some of these gaps in the index. Yes? Yeah?
Is there a particular pattern of insertions that you need to minimize the fragmentation?
That's a great question. That's a great question. I mean, some patterns are certainly better than others. If I insert everything in order, or close to in order, that's going to lead me more towards the situation that I'm currently in. So your idea of doing greatest, least, and alternating back and forth, working away from both ends, I think I don't have the proof, but it seems like a reasonable place to start thinking about that. Yes. The order that you insert things absolutely does matter. I could have 2 B+ trees with the same values in them with a different structure just because of the order that I inserted those values. Absolutely, that can happen. Great questions. Any other questions? Any other questions about this? We still got about half an hour left, so what do you guys want to work on next? Anybody got another problem they want to talk about? Another concept? Yeah, what's up?
You're going to quickly talk about when you talk about B equals 2 equals 3.
I'm just going to fix that slide.
Okay.
That slide is busted. I'm going to fix it after class. Yes?
Can we go over the example problem with a query tree?
With the query tree, sure. Is there one in particular you were thinking of from the exam?
Well, I was just looking in the exam 1 review, there was a query tree question.
Oh, okay, in the review slides, okay.
Could also do what we've already done.
Oh, okay. So we have to write some queries first before we can construct the query tree. So that's all right, we can do this. I've given you some sample tables here, and I want you to write some SQL queries So we have to do this part first. I can't construct the tree. I guess I could construct the tree without the query, but we got time, so let's write some queries. I'll give you guys a few minutes on this one. There's 4 examples here. Write some queries, and then see if you can construct a query tree for those as well while you're at it.
I just gave the tables names. So I named the first one.
Oh yeah, so the tables aren't named. Come up with, I mean, the left table is users, the right table is movies, the table in between is, I don't know, watched movies or something like that.
Well, so I don't know. Yeah.
Because we always table the left. We always table the left. There's 4 values. Split them in half and then take them up to the left. Okay. This isn't a valid tree under our. Yep. So you've got 4 values, and split them in half, and look at the one directly to the left. Yeah, what's up?
This is kind of like going back to the question on deletion. I think I figured out, like, based on practice, how that this is the case, but I figured I was looking to push through the deletion. I was trying to consider like a non-trivial case when there was like more than one child to look from. But then I thought maybe it would be a cascading push through. But then I look back on, I think no, even in deletion you still only want to consider the one immediate left and immediate right.
I believe that's it, right?
Oh.
Yeah.
Now for me, what I did is that at first I said select the name of the movie from movies join users to movies where the movie ID equals users to movie ID, and then I left join that result on the users by users to movies, where the user's first name is not null. Because if I join these 2 tables together, and like if I start with this, then I end at this, and I have no user ID. If I don't have a null entry, if I don't have nulls for first names associated with that, that means that that's a movie that that a user hasn't watched. But if I have one for all, that should be a movie that I believe that's how I should have a movie that all users have seen. I could be wrong, but this is you should also use last. But the idea is that you're going to try to join all of individuals to find to their and so like then you're going to try to match like the first name to join. So like for example, 2 is not in here, so 2 is not going to have anything joined up in. I used the outer join, which means that I'm not going to have an entry for 2 because it's gone.
Has to be at least half. So if I had, if E was 5, it has to be at least half.
It may need to be pointing.
Think about users, movies.
The first rule should eliminate any movies that haven't seen by any movie, because okay, those obviously haven't watched by movies. And then the left join will eliminate all except the movies that hopefully just narrow down to example watching.
So we are getting like kind of back to
Doesn't differ by how many so then you'd already have like it like count like you don't need to have the
Okay, here we go. Let's write some queries and make some query trees. What's the name of each user? So I know there's two clauses that I always need, right? Select and from. So if I want to get the name of each user, what do I need to do? Select fname, lname, oops, from users. There we go. One down. What would the query tree look like? So query tree, what do I start with?
Tables.
Tables, and those go at which end of the tree?
Bottom.
The bottom. So I just have the one table, which is users. What else do I have? Part of this. What kind of relational operation are we looking at? A project. A project. What's the symbol for a projection? It's pi. Fname. Lname. Here's our query tree. It's very simple. It's a simple query, right? There's not a lot going on in this query. The query tree is also simple. How do we optimize this? I mean, come on. It's a, there's not much going on here. It's already probably as optimal as it's going to get. All right, let's see if we can get some more complicated ones going on here. Next question, how many movies have been watched by all users? So this question is a little ambiguous, right? Am I asking you, of the movies in the system, how many of them have been watched by every single user? Or am I asking you, like, what's the total number of movies that everybody has watched, right? I think I probably intended the latter, but, we could still answer it the first way as well. That's totally fine. If we mean it just like, what's the total number of movies that have been watched in the whole system, right? How many times have people watched a movie? What would I need to do? Yeah.
count the number of records in the table.
Count the number of records in the middle of the table. That's it. Select. So how do I do that? Select, count star from watches, sure. Or watched, or whatever you want to call it, that's fine. That's it. That's it. If I'm interpreting the query as just the grand total of the number of movies that have been watched, that's it. The other way, what movies have been watched by every single user in the system, that's actually a lot more complicated. I've been sitting here thinking about how you would tackle that query, and I don't want to say it would be impossible with the concepts that we talked about, but it would be very difficult with just using the stuff that we talked about in class. That would be a very difficult one to do. Yes?
This one would also duplicate the IDs.
So we could use distinct here, but that's answering a slightly different question, right? Again, it depends on your interpretation. This is an ambiguous question. So I certainly would accept that as an answer. I could say distinct, sure. But actually, if I say distinct, we have to be a little bit careful, right? What does that actually mean? That means that I'm looking for a distinct user ID, movie ID combo. So what am I really filtering out? I'm filtering out
Watches by the same
duplicate watches by the same user. So my Netflix is filled up with watches of The Matrix because it's my favorite movie of all time, right? It would filter out all of those watches of The Matrix, just the first one, because who would watch the second or third one, and just give me one distinct watch for that movie, right? All right. How many movies has each user watched? That's a more interesting question. I know I didn't make a query tree for this, but let's do the next one and do a query tree for that one, because this would be a fairly straightforward query tree. Let's do the next one. So what do I need if I want to know how many movies each user has watched? How does that change? We can actually start here, right?
How would you write the count in the query tree?
How would you write the count in the query tree? Well, I think we're going to have a count in the next one, so I'll show you at the next query. That is something that I wanted to talk to you about today. We'll see that for this next one. How many movies has each user watched? I still need a count, but now I don't need a count of everything. I need a count that's broken down by user. So how do I do that? I need a group by. But what am I grouping by? User ID is probably the easiest way to do it, right? Group by UID. Group by UID. So now I'm going to get, now what's my result going to look like though? This is the question. I'm just going to see just one column with numbers. I'm not going to know who actually is associated with those numbers. What if I wanted to know who was associated with those numbers as well? What if I wanted to get the names attached? What would I have to do? I'd have to do a join. The names are in a different table. I'd have to do a join. So let's do that. I'll put that group by back in a second. I'm just making room so I can do this join. Join users on. And the link is the user ID, right? Watches.uid equals users.uid. And then I can still have my group by down here. Group by. Now when I say UID, right, the chalkboard can't complain, but if I did this in the computer, it would complain. Why?
Because there's two.
There's two of them. There's one in the watches table, and there's one in the users table. Does it matter which one I pick for this purpose?
No.
In this purpose, it doesn't actually matter which one I use, but I do have to clarify, right? Otherwise, the computer thinks this is an ambiguous statement. It's going to complain about that. So I do have to clarify which one I want. Users.uid. And then to really round this out, I'll add the first name and last name to my select. There we go. That's a good query. That's a good query. Yes?
Since joins are fully commutative, it could have just as easily been join user watches on. It could have been from users on watches.
Yes, I can flip the order of these or the order of this, and it still is equivalent. Now, if I had done a different kind of join, that wouldn't be true. What kind of join?
Left join, right?
Left join, right? An outer join. If I had done an outer join here, then I cannot just flip these without having an effect. Then it does matter. But for an inner join like this one, I can flip the order. It gets me to the same place. Let's make a query tree for this one. I got a join. I've got multiple tables now, right? Got multiple tables, so I'll put those at the bottom of my tree. Watches and users. What comes next? I mean, we could just do it in order, so we can actually optimize this later, right? If I just ask you to make a query tree, it doesn't matter if it's optimal or not, if you run it through that optimization or not. So let's just make one that's complete, and then we can talk about how to do optimizations a little bit later on. So I see the join next. I'll just do the join. Okay. Here's my join, and I have to specify, what the condition is. UID equals UID. Then I've got this projection here, right? F name, L name. Do I have to do anything in the projection for this guy? This is where things get a little tricky. We haven't talked a lot about these on query trees yet. Actually, the way that we do aggregates with a query tree is just via a generic function. There was a slide about this when we talked about it. So I would just put in a function. It's like a fancy F where I specify what the aggregate operation is, count star, and then if I have a group by, which I do, I'll put that on the left-hand side, UID. I'm grouping by user ID. So if you have an aggregate, you include it as a function. Let's talk about optimization. Is there anything I can do to optimize this query tree? Yeah.
The one thing is you're only interested, as far as like watches goes, you're only interested in the watches UID, so you could move your project down to that.
I can do some work with the projections. That's right. I'm trying to project stuff off of this tree as fast as I possibly can. So the only thing that I need from this table is the UID column. I don't need the MID column. So an optimization really would insert another projection here on UID before the join happens. I can't do the same thing for users because I need the UID and the first name and the last name. I need the whole table to do this. So I can't insert a projection here, but I can insert a projection here to get that MID table off as fast as possible before the join. I think in terms of optimizations, that's about it. If you want to talk about aggregations for optimization, which we didn't do, actually. I didn't include that in our discussion of optimization, but aggregations almost always have to go last. Almost always. I can't get a proper count until I've filtered out everything else, right? Or I can't do a proper sum or a proper average until I've filtered out all the values that I don't care about. So that aggregation with the group by is almost always going to go last in terms of optimization. Any questions? Any questions? We got one left. How many times has each movie been watched? That's going to look actually very similar to this query, is it not? It's another count, but this time instead of grouping by user ID, I'm just grouping by MID instead, the movie ID. Otherwise, it looks very similar. I'd be joining to the movies table instead of the users table, and grouping by the movie ID instead of the user ID. So the end result's going to look very similar to this one. Any questions? Yeah.
Can you explain that inner join part?
The inner join part? What about it?
Like, there's more UID information in the bottom.
Sure.
So are there going to be null values?
Are there going to be null values? Do I get null values with an inner join? No, I do not. I do not. And even if I was using a join that could give me null values, so if I was doing an outer join between the users table and the watches table, would I see null values? If I did an outer join between those two tables, would I see null values? If I do an outer join between watches and users, would I see null values?
No.
No, why not? Yeah.
Because every user ID is represented in the watch table.
Every value in my foreign key table has a match. I only see null values when I don't have a match. When I don't have a matching value in the table. So regardless of how I join these two tables, I'm not going to see nulls. Now, if I look at these other two tables, if I did an outer join between movies and this watch table, then I might see some nulls because there's a movie that nobody's watched yet. Right? Number 2 doesn't show up. So I could see some nulls if I did an outer join in that particular situation. Any other questions? We don't have too much time left yet. I'm sorry? Maybe. They're certainly possible. We talked about them. Did I see another question? Yeah.
goes all the way up to the top usually. But it's probably not perfect for this example, but let's assume that that middle table is massive.
Okay.
And by doing, and just go to the subgroup and stuff like that, let's assume that's massive. So by choosing a priori on that table and didn't count and joining the user ID table, you might be able to gain some efficiency.
I see the point you're making. Yeah.
Yeah.
So the question was, what if this middle table here was gigantic, right? And so then I would actually probably be faster to do the count first and then the join afterwards to reduce the space. In this case, it's possible to do that because we have the user ID here, but actually the way that we've written the query, because I use the users table UID here, prevents me from technically doing that because I haven't joined those two tables together yet. So the group by column isn't part of my result relation. If I had decided to group by the UID in this table, then that could probably be done. Yeah, probably be done earlier on in the query tree. So yeah, I was very careful not to make the claim that this will always be at the top, just that it oftentimes is at the top. Great question. Any other questions? Yes. The order is swapped. We read these from the bottom to the top, so I'm projecting off UID first. When we aggregate? I'm not sure I understand. Oh, you're right. I forgot that UID was here. So this projection would actually have to happen afterwards. I apologize. That's actually a great observation. I can't project these two off here because I need the user ID as part of this aggregation. So we got to swap the order of that. Thank you. Good catch. UID count. And then the projection. Cool. Thank you. We got like 3 or 4 minutes left. Any quick questions that I can answer with the time that we have remaining? Yes. We combine what? I'm not sure I understand the question. Can we? Oh. So does it matter what I put inside this parentheses? Whoops. It really doesn't matter what goes in here, right? Because every single row is going to have that value. Every single row is going to have an entry in that column. So it does not, there is one exception where I might see a value put in here, which is if I'm counting distinct things. That's the one time where I might see something in here that's not a star. But if I'm not counting distinct entries, I'm just going to see a star in there. It's the easiest way to represent it. Yep. Question in the back.
Real quick, so when we talked about insert, search, delete, and modify for each file, of that, we said that if we're adding something to the end, then time would be constant.
Yes.
But if we were searching to find the first open slot in the header, then it would be end. So my question is on search. We said that search would be end because we need to check the header, but then I get a little confused with shouldn't we know where it's located?
In our implementation, we actually did know where the tuple was located in Lab 1. That is true. We knew tuples had a location, but I might not have that information when I'm performing the search. So if I don't have that specific information, I have to go check every single one.
So then, just a really quick follow-up. If we're modifying something, we said we would delete it and then add a new item.
That's one implementation, yeah.
So if the record knows where it lives, I guess, so my question is, would that be constant time? I suppose it knows where it lives.
If it knows where the record is, then yes, I can just jump right to that location, delete it in constant time,
And
and
then if it doesn't, both of them would say.
then we have to do a search to find the records that we're deleting. Or actually with a, yeah, we have to do a search to find what we're deleting, and
And
then
then we would add it in the same spot, so that would be next time.
you could add it in the same slot, yes.
Okay, thank you.
Yeah, no problem. If you have more questions, I have office hours tomorrow, almost all day. So from 10:30 to noon, and then from 1:30 to 4:30, I have office hours. So come talk to me about this. Be happy to answer any questions you have. And I'll see you on Thursday for the exam.
It's just one quick.
Why would it go away though? We still need to perform that aggregation.
I'm just confused on how they optimize query trees.